force equals 0 problem. We know it's 0 because the children are traveling at a constant velocity. So a quick picture of this, I've got ground, sled, and somebody pulling. So now I go get the details. The children and the sled have a combined mass of 30 kilograms. Combined mass, 30 kilograms. Based on the mom's height and the rope attached to the sled, the rope will make an angle of 40 degrees with the horizon. If the mom pulls with a force of 150 newtons. All right, this is it. That's all the information we need. So I don't know what you're doing wrong. So look at your picture first. I have to draw a free body diagram. There's going to be a bunch of arrows here. I'm going to start with a dot representing the sled. I'm going to go through a list of forces, and let's face it, we've only had 4 or 5 forces. It's gravity, tension, normal, friction, and something resistive. The only outside thing is every once in a while somebody adds a force, an applied force, something that's in the problem. So let's start with gravity. Is there a gravitational force that matters in this problem? Yes. I draw an arrow downwards. I know quite a bit about this force. So what are the next things we talk about? I'll put just a W there. Weight. But I know that that's going to be mg. I know that's going to be 30 times 10. I know it's going to be 300. I know all of those things. You should know them too. So go on to the next thing. Is the sled in contact with any surface? Yes, it's in contact with the ground. The ground must apply a normal force to the sled. That force has to be perpendicular to the ground. It has to be upwards. It's less than the weight. Why? Because I know the mom's pulling up on the sled later, but I don't know how much this one is. Is there anything pulling on the sled? Yeah, the mom. They tell you in the problem, mom's pulling on the sled. 150 newtons. Angle 40 degrees. Again, what are you not doing here? This does not look balanced. Does it look balanced to you? But it has to be balanced. The problem says so. So I need another arrow. What else is left? Well, is a box sliding across a surface? Yeah, there's friction. Friction must oppose the direction of motion. It's going to be perpendicular to the normal force. Has to be. It's parallel to the surfaces. Yeah.
Your angle of 40 degrees, how come it isn't on the other side? Is that straight explained since the complementary, or like the interior angle?
It says 40 degrees with respect to the horizon. They tell me the 40 degrees with respect to the horizon.
Okay.
Does that make sense? So I don't have to change anything about it.
Okay. Thank you.
You're welcome. All right, I need a coordinate system. Your choice is either to make the coordinate system aligned with the acceleration or make the coordinate system aligned with as many forces as possible. Now, I know you sometimes aren't thoughtful about these decisions, but this decision matters. There are 3 forces that are all perpendicular with each other. I'm going to try and make my coordinate system aligned with them. Today, we're going to do some where we're not going to have them lined up like this, so I need you to be paying attention and not throw away that. Did you write anything down just now? If you got something wrong here, did you write anything down to help make it better next time? So coordinate system, are there any forces that aren't aligned with the coordinate system? Looks like there's one of them. Do you see the one that's not aligned with the coordinate system? So I'm going to need to break this up into its components. There will be a component in this direction and a component in this direction. One of these gets sine and one gets cosine. So this one's going to be 150 sine 40 because it's the opposite side. And this one's 150 cosine 40 because it's the adjacent side. once I've done that, that was necessary just to be able to get my one-dimensional portions of the problem. So now I've got all my forces in one dimension. Any questions about that? No questions, but we got a solid 50% on this test. Maybe all of them were from the next question. Net force in the x direction equals 0. Net force in the y direction equals 0. I see two forces in the x direction. 150 cosine 40 minus friction equals 0. I can get friction from that right away. All right, do you see that? All right. In the y direction, normal is upwards, it's positive. Plus 150 sine 40, which is also positive. Minus weight, because it's downwards, equals 0. Can this be solved to find the weight? I'm sorry, to find the normal force. I mean, it looks like it clearly can. I think we're done with this one. Any questions about it? Go ahead.
When like if there's like a small decimal, like what are your like round expectations?
I think you should always hold on to as many decimals as possible in intermediate steps of the problem. But at the end of the day, your answer should be in the same number of significant places. And the most number of significant places I see here is 3. So I don't need anything more than that. But you're not graded on that so much. So, you know,
But like would it be considered wrong if I put 2 or 3.5?
no. All right, let's do the next one. A child pushes a box along the ceiling. He pushes in such a way that the box stays in contact with the ceiling while also sliding across the ceiling at a constant velocity. All right, all the same things. So I need a ceiling. I need a box. The box is 2 kilograms. And a child pushes at an angle of 75 degrees with the horizontal. So I'm going to draw something that indicates the child's force. (75 degrees) and 30 newtons. Right, Christian? Okay. Just checking. Okay. All right, so we're going to draw a free body diagram after recognizing this is a Newton's first law problem again because constant velocity. So I reduce the box to a dot, start talking about forces. Does the box have the force of weight acting on it? Should I draw a downward arrow? I should. The weight is mg, or 20. 20 times 10, or 200 newtons. Is the box in contact with any surface? Yes, the ceiling. The ceiling applies a force that is perpendicular to the ceiling. I can't tell you how many people have a normal force pointed up who got this wrong. What?
You put 20 kg for the mass, but it's 2.
It's 2, sorry. All better. The normal force has to be perpendicular to the surface. That means downwards. There's a pushing force, and I just have to go with it because they gave it to me. 30 newtons at 75 degrees with respect to the horizon. This This doesn't look balanced, but I have one surface sliding past the other, so I'm thinking we have a frictional force this way. That's what I was looking for the free body diagram. Questions? All righty. I need a coordinate system that can be used to solve the problem. I'm going to choose one that is aligned with the most number of forces. That ought to work. So positive x, positive y. Now let's see. I need to break off my off-axis force into components. So probably a force this way. And probably a force this way. I'm thinking this should be 30 sine 75, and this one should be 30 cosine 75. I am blowing through the trig now. If you're not able to, and you have questions there, you should be asking. But most of the mistakes I saw weren't this. But once I've done that, I kind of don't need any of that anymore. I know you can't just do that on your paper, but you can clearly articulate and label everything. So net force in the x direction equals 0, and net force in the y direction equals 0. In the x direction, I see 30 cosine 75 minus friction equals 0. In the y direction, I see 30 sine 75 minus normal minus 20 equals 0. That's it. That's the extent. Solve that for F and N. So again, all I want you to do is take this situation, assume that there's no friction, and find the acceleration of the calculator down the ramp. Again, just start with the free body diagram. Now, I'm going to say steps out loud and believe that you should be done in a reasonable amount of time. So we've gone through, we've identified all the forces acting on the object, we've identified which forces matter, which ones don't, there's no tension, no friction. We've made sure to indicate that the normal force is perpendicular to the surface and that weight is straight down. You guys are supposed to be putting in a coordinate system now, and you should make as a high priority a system that is aligned with the acceleration. Once you've done so, there's going to be a force that is off axis. You need to break that force up into components. I want to come by and see your work. One of the first things I noticed for a lot of you was having difficulty deciding what you wanted to do when it came to drawing in your coordinate system. But the box goes this way. That's the direction the box goes. Now, our picture can only have forces on it. But because the box goes this way, we want our coordinates to be in that direction. The coordinates are placeholders that help us divide up our forces into meaningful values. I'm not saying these things to try and, to be esoteric. If it's on an inclined plane, it's going to be better for you if you line stuff with the incline and not the horizontal. What's happening to the box is happening on the incline. So I'm going to make the x direction the direction of the incline. I'm also going to make the y direction perpendicular to that. Now I'm working hard to make sure my lines look perpendicular. And a few of you I know are not understanding why I'm being so careful. Look, I should be able to take this level it off, and it should look like the normal XY stuff that you guys see in your other classes, with one of the arrows looking unbalanced. It is a part of this force that is dragging the calculator down the ramp. And it needs to look like that. So if it makes more sense to you to draw it and turn it, then do so. Because I saw this next problem on a bunch of papers. My next goal or job is to take the off-axis force. And I had to explain that to some folks. Off-axis means it doesn't line up with X or Y. So can you tell me which one of these arrows, the N arrow or the W arrow, is the off-axis one? W is the off-axis one. All right, so I do need to decide which of these is 20 degrees first. And I told you how to do that. It is the one that is between the weight and a line drawn through the normal force. This is weight. This is my line drawn through the normal force. So here is 20 degrees. Now, here's where I want to point out some mistakes I saw. I need an arrow this way and an arrow that is perpendicular to that one. Those make the right triangle. All right. So this is just a basic inclined plane question. What I want you to tell me is, with the information I've given, figure out what the acceleration of the calculator is down the ramp, or down the book. I think it's pretty clear that the calculator accelerated this way. Gave you a framework to start this problem yesterday. But this one, is it a first law problem or a second law problem? Second law problem. You are solving. You will get a numerical answer for this. So I want you to work towards. So you only have 2 arrows to draw. At this point, I hope you recognize, for the most part, unless the problem dictates a force to you, that it's gravity, normal, tension, and friction. That's what we've seen on all of these problems. So although I gave you a big exhaustive list of other stuff, yeah, those things are there and you need to be able to do them and all. These are going to show up. They show up all the time. Recognize that. This is example, number 7 for us. I'm trying to throw as many out there as I can. And we did this exact question yesterday without friction, so you have a model to look at. So I'll start by taking that box, reduce it down to a dot. The only arrow that you always know is in the same direction is weight. So get it drawn. Now, there's no cable, strings, there's no tension. I tell you there's no friction. But is it touching anything? The moment it is, there's a normal force. And I'm drawing it over there on the incline because I'm trying to make it look as close to being perpendicular to the actual picture as possible. This is it. Those are the only 2 forces. So before anybody says, well, this is a really tough one, Mr. Shelton. No, 2 arrows, that's all you had to draw? Now, we're not quite done here. We haven't done anything that would actually solve the problem, but do they look balanced to you? When I say that, I mean, I don't think it looks balanced. For every left, a right. For every up, something down. Does that look like what you see here? I see something that looks unbalanced. And our object is constrained, meaning our object's not going to suddenly just fly off this way. It's going to go down the ramp. We know what the object's going to do. So bring that to the table here. I have to solve the problem. And I only have one-dimensional math, so I have to pick what direction I want to draw coordinates so I can do trig. That's going to be a part of the problem. This is not random. And I saw 3 of you kind of randomly draw lines here. It's not random. I'm telling you exactly how to do it. I'm saying if you can, line up one of your arrows with the direction it's going to accelerate. If it's not going to accelerate, line up your arrows so that almost everything is directly aligned with an X or a Y. There's only 2 arrows here. So I'm either lining up something with the normal or I'm lining up something with the weight. But I know it accelerates, so I'm going to choose to line this up with the ramp. Trying to make it as close to the ramp as possible. There we go. Because that's the direction it accelerates. And by lining it up with the ramp, I'm automatically lining up the other force with the normal, because the normal is perpendicular to the ramp. Now, look, if I were to straighten these out, does it look like the object is being pulled to the left now? Yeah. If it makes it look easier for you, then turn yours. If that makes it look easier. I generally don't, but for the rest of this example, I'm going to leave it turned like this. Now, I walked up to one of you yesterday and I said, are there any off-axis forces? And you said, I don't know. It was in this class. Off-axis forces. That means that it doesn't line up with either X or Y. Is there one of them here that is off-axis? Yeah, there sure is. It's very clear, right? So the one that's not lining up with X or Y, that's the one that I need to deal with. I need to draw a triangle around it. But before I do that, I need to know where the 20 goes. Is the 20 going to go over here or over here? Right, it makes a difference. So do you know where to put it? I told you to write something in your notes to help you here. And I'm gonna say it again. I want you to be able to figure it out. But that hasn't worked out for me in the past year. So I'm going to tell you. Find the weight. Draw a line through the normal force. And that's where the 20 degrees goes. I've drawn a line through the normal force, and I found the weight. You put the angle of the incline there. Look, you're going to have this on your exam. They're going to ask incline plane questions. And it's going to be in multiple choice where you have to work fast. Now, here's where turning it might be of help to you. Because I did see something weird on a couple of papers just a few minutes ago. The right angle has to be between the 2 components. The right angle has to be here, not here. That's important because if you don't turn it like I just did, and you leave it the way it was, when it was arranged to look like that, there are people who will take and make this particular vector here. Can't do it. I'm going to try. They'll place it like that and draw their triangle like this, and everything will be wrong. They'll get all the sines and cosines wrong. So part of the reason I turned it for this example was that you can see quite clearly where that right angle goes. The vector that you're breaking up is always the hypotenuse, always. So from this point forward, this side is going to be the weight, sine, the angle. And this side is going to be the weight, cosine, the angle. If you want to put something into your notes that's useful, that unless something weird's going on with the incline, the part of the weight that is into the incline is cosine. And the part of the weight that is causing the acceleration is sine. It is the one that's pulling the object down the ramp that's going to be sine the angle. If you want to memorize something to make it fast, weight sine theta down the incline, weight cosine theta into the incline. Weight cosine theta is causing there to be a normal force. It's the part of the weight that's pushing into the incline. It's creating the normal force. Weight sine theta is causing it to accelerate down the ramp. All right, let's put that away for a minute. Net force is in the x direction and net force in the y direction. I didn't say it clearly, but I'm making this the x direction and this the y direction. So MA goes with the x direction and 0 goes with the y direction. This is because we lined up the x direction with the acceleration. So that leaves us with weight sine 20 degrees equals MA, and normal minus weight cosine 20 degrees equals 0. Now, there's not much left to do, but there are a few little things. Like, do you notice that you have enough information probably to solve for the acceleration? Doesn't look like it maybe, because I didn't give you the mass of the calculator. But we can substitute mg in for weight. So when we do, we'll get mg sine 20 degrees equals ma. Do you guys see that? Do you see why we can solve for a now? Because the m's cancel. It's going to be very often that m cancels out in these problems, and you won't be given mass. So don't be confused. Work the problem. It's likely m is going to cancel out somewhere. We can't find the normal force because we don't have m. To get a force, you need mass. So we don't have an answer for normal force, but you can certainly get an answer for the acceleration. That's where you get 10 times the sine of, 20 degrees will give you 3.4. All right. You needed to find an acceleration. That's all Newton's law can do. So again, we start with this system horizontal, like so, and we tilt it so that the ramp makes an angle of 20 degrees. How far does the spring stretch? How far does the spring stretch? I'm using this example because you can reuse 2/3 of what you just did for this problem. But before you get started, is this a first law problem or a second law problem? First, that's right. The spring's going to hold the system in place. And of the 4 forces I talked to you about, gravity, tension, normal, friction, what's the spring bringing to the problem? Tension. So you're just going to add a force to what you just did. So I shouldn't have to wait very long. We're going to draw our free body diagram. We're going to do so quickly because we know the kinds of things to put here because we just did this problem. So you grab that ruler and we start with a downwards arrow. That one we know, right? What do you label that? Weight. Excellent. Move on to our next force. Normal force. It's got to be perpendicular to the surface. So I'm going to try and make it perpendicular. I'm doing my best to kind of line it up here, make it perpendicular. So I want this to look right. So I think it looks pretty right. So I'm going to move that sucker over there. There's my normal force. Might be a little long though. All right, so got my normal force. Going to label it so everybody's happy. Normal force. So I have to draw one more force in there. What's that force going to be? Tension. Along the ramp, right? So this is going to be perpendicular to the normal force, and it's going to line up with the ramp? So I think it's pretty close. I'll do a little better job there. There we go. I'm going to call this tension. I'm going to work the problem, but I'm hoping you'll see that this problem is really similar to what we just did. I'm going to draw my coordinate system in, and although it's not accelerating, do you notice that two of these forces are perpendicular to each other? So I'm definitely going to use the same coordinate system as before because it lines up with two of the forces. So I'm going to make this my x direction and this my y direction. It seems clear to me, but I know it doesn't always seem clear to you, but I have to break the weight up the exact same way as last time. So I don't want to think about it very much because this is going to show up so often. There's my 20 degrees. Put it between the weight and the line through the normal force. I'm going to draw an arrow to indicate there's a component in the y direction and another arrow to indicate there's a component in the x direction. But I'm not going to think about this very much either. I know that this one has to be weight cosine 20. And this one has to be weight sine 20. Again, I'm telling you, get this into your notes that for most inclined plane problems, you can break the weight up the same way every time. So you're not having to think about it that hard. I want you to be able to jump down a couple steps and realize that in this problem, weight sine theta is going down the ramp and weight cosine theta is going into the ramp. So I can start with this part next. Net force in the x direction equals 0. Net force in the y direction equals 0. Which forces are in the x direction? Tension and weight sine 20. Doesn't really matter which one of those I make positive or negative, right? I'm just making this one positive because that's one that's sticking out there. I guess I'll make this one positive. So I got normal minus weight cosine 20 equals 0. Now, we're close to the end. But the question I was asked was, how far does the spring stretch? Which means you've got to bring something else to the table here, something else. It's going to be on your equation sheet. I've given it to you on the sheet that you have. You have to bring to the table that the force from a spring is equal to minus k delta x. And you have to know that the negative sign is about direction. We already know the tension is up the ramp. We know that from the problem. And we know in this problem, the tension comes from a spring. We know that. So if we can figure out the tension, we can figure out what's happening with the spring. So tension equals 0.2 times 10 times the sine of 20. Right, you can work that out. You got calculators. You can get that it's like 0.68, I think. 0.68?
Yeah.
Well, now you can figure out how much the spring stretches. You can put it over there and find out delta x. I gave you the value for the spring. The Newton's law part of this problem, it finished here. Newton's law can tell you a force or it can tell you an acceleration. In this one, you needed to find a force. But ultimately, when we're done, we're often going to use that force to find something else. So I'm going to say 0.68 equals minus 20 times delta x. don't really care so much about the minuses and pluses. They're about direction. We know the direction the spring stretched. But this tells me how much. So it looks like, I'll just find it here, but something 34, 0.034. So that's meters, because it's delta x. So it's 3.4 centimeters. That's how far it would stretch the spring. All right. I know it's a lot. I know I'm asking a lot of you, but this stuff is tough. And I want to talk about one more thing, and then we'll be done for the day. Well, it's negative because it's down the ramp. Like I was trying to say, I'm not too worried about the positive or negative. We know that it goes down the ramp, right? But we just asked, how far does the spring stretch? Does that make sense? So if you can interpret that negative sign indicates down the ramp, you're doing just fine. And there'll be much rejoicing. Yeah. I want to talk to you about friction. And that's a major topic for tomorrow. But I want to introduce something about friction that's in your homework. If you've started your homework, you'll notice that several of your questions say something about friction is some percent of the normal force. If you started your homework, like question number 2, I think is where it starts up with that. Saying something like friction is 60% of the normal force. There is no friction without normal force. There is no friction without normal force. So, friction is always a percentage of the normal force. That's a true statement. It's not just a made-up thing for the problems. Friction is created because of normal force. And it's more than just that. In chemistry, you might have heard the word adhesion or cohesion, or you've heard of cohesive tape, stuff like that. Friction is a measure of the stickiness of a surface. This percentage is how sticky the surface is. Rougher surfaces generate more friction, and slicker surfaces have less friction. So an iced surface would have a very low percentage of friction compared to normal force. While tarmac and tires have a really high percentage. And it's not just about one surface, it's about two surfaces. I mean, if you're an ice skater, you're putting steel on ice, because if you put something that was rougher on the ice, like rubber on ice, it would stick more than the steel would. But if I want to make sure my tires don't lose traction, I use synthetic rubber and asphalt, because they're very sticky together. You get almost like 80-90% of the normal force can be transferred into friction between asphalt and tires. But we call this percentage, it has a name, it's called the coefficient of friction. And it has a symbol, the Greek letter mu. All right, we're going to stop there.